Hello, hello, hello. So today is our day 5 and this is Python. We'll be starting using Python and then we'll go to Rust later on because Python is so small that we can cover it up very quickly. So let's cover it up. So this is Rust and Python to learn, data science and machine learning alongside everything else. So from past 2 days, we were only doing benchmarking. So today also we'll do benchmarking. Let's see. So plan acknowledged and we have a plan. All right. So this is day 5, Python systems thinking. So topic is why NumPy is faster than pure Python. Now we begin from fundamentals, no assumption. And we have studied multiple reasons why NumPy is faster than pure Python. But let's go again. So part one is why is a Python loop slow? So what actually happens in a Python loop is that this looks simple, but internally, each iteration involves load Python object reference that we know, type checking, yes, method lookup for add, yes, unboxing and boxing integers, didn't know that, add boxing and unboxing integers. After that, a reference count update. Yeah, reference count update. And then interpreter dispatch. Now, Python integers are not raw machine integers. So they are Python object structures, something like this. Type def and then the structure, then the Python object head, then long object I value, and then Python long object. So each integer is separate heap allocation, has metadata, has reference counting overhead. So every addition is not just add rex rbx. What is this? This is machine code. Like uh, you know below C. What is C? Assembly. Yeah, this is assembly, not machine code. This is assembly. So we add RAX and RBX to memory together. So it is a dereference pointer, check type, and calls function, allocates new object, and updates references. Now this is expensive. Part two is that why is sum faster than manual loop? Why is sum function that is faster than doing the sum in manual loop? So sum is implemented in C inside C Python. So it still iterates element by element, but loop happens in C, which is fewer Python level dispatches and less bytecode overhead. So manual loop is Python bytecode per iteration, and sum is C level loop. Still object based, still boxed integer, but fewer interpreter cycles. Now part three, why NumPy is much faster. Now the real system inside is that NumPy arrays which store element in contiguous memory like side by side and uses raw C types like int64, float64, no per element Python objects. And memory layout is something like this: 8 byte, this is first, 8 byte, another integer, 8 byte, third integer, fourth integer, and so on. Not like contiguous pointers, but then pointers are pointing towards the object that are needed or required. It's not like this Python object. So consequence of that is that CPU cache friendly. The NumPy is CPU cache friendly because CPU does not just call for one 8 byte. It calls for sort of 64 bytes in which there are 8 times the 8 bytes. So it calls for 8 uh, together, 8 consecutive digits together. So it is again CPU cache friendly because cache gets locked and then it can be easily computed. No pointer chasing. There is no pointer chasing like Python objects, and then no dynamic type checks. All right, and then vectorized SIMD instruction possible. Uh, Single input, multiple, something like that, SIMD, and then compile C loops. This is why NumPy can be 10 to 100 times faster. Part 4 is that CPU cache line concept. A modern CPU load memory in blocks, typically 64 bytes. That's what I was talking about. If elements are contiguous, one cache line fetch gives 8 float 64 values, and operation happens without new memory fetch. And if elements are pointers, the cache miss likely for each dereference. because cache will then just get some eight pointers, and then you have to dereference those eight pointers to, so there's no cache benefit over here in Python objects, and it has more memory latency. So memory latency is the far, far greater than CPU arithmetic cost. So this is the cost, memory latency to, dereference those pointers. Now that is the key. Now you implement day5 benchmark.py. Let's do it. Uh, what is it? Day5, and again, oh sorry, day5 benchmark, bench benchmark dot py. All right, this is our day5. Now task is to generate 10 billion numbers. All right, and from measure using this from time and import pref counter. That's what we did past 2 to 3 days. So benchmark is likely to be manual Python loops and built-in sum loops and NumPy NP sum. Structure will be n is equals to sort of 10 million. So I can directly import the time, or we can just import pref loop from time. So from library time, we should import pref. Oh, it's not pref, it's perf, perf of COUNT counter. All right. And then we'll describe a constant at the top, that is 10 million, which is this. These underscores will be ignored, so no worries for that. And now we have to benchmark, first of all, Python loop. So how benchmarking happens, first of all, you start the timer, and then you have to end the timer, and in between you do the operation from which you are trying to benchmark. So we do time dot perf perf COUNTER counter, and over here to time dot perf COUNTER counter, and then manual Python loop, which is very long, so I won't be like, I'll implement it, but I won't be doing it. So for I, instead of in range, we can do in range, but we are not like calculating the range time, because range is a Python object, so it also takes times to go to the length of 10 million. So it takes times. Instead, what we do for this is we create a list called data. So we'll have a list of range, n, and we'll store that as data is equals to this. Now for I in data, what we'll do is do something wrong. For I, oh, did we do something wrong? I think so. Is there any implementation code? Ah, it is not there. So what? Measure using and built-in sum and np.sum. This is our task, so we have to do it. Ah, there is this in data, and for I in data, what do we want to do? We want to implement manual Python loop for what? Built-in sum function. So we are adding something. Are we adding something? Are we adding something? total. All right. So let's say there is a variable total, not total, total TOTL, which is 0 for now. And we say that we have to sum it manually, which is by loop, like this. Now, this is our first thing that happens. Another time which the Python loop takes. So we'll say py loop takes some time. Time is equals to end minus start, and that's it. After that, we'll say print whatever the value is. We'll use f directly. So time took to run by loop time to run to sum using by loop is some is something like by loop to and time. Is this all right? I think so. There shouldn't be much of error. Oh, sorry. Let's interrupt this. First of all, damn it. You know, it's too for less data set so that we can get results faster. So just oh, there is time. What is the name error? Counter of start is equals to time dot erf counter. Time is wrong. Time can never be wrong, yeah. Name time is not defined. So instead of, I guess, doing this, how about just say import import at time. No, that's what we did earlier. Just comment it out. Run it. Yeah, see, it works. From time import this. Why didn't this work? Why didn't this work? PERFCOUNTER. Do we have to use this? Yeah, we don't. So why doesn't this work? From time import per getting this and import time. Ah, we can do this also. It's time pointer. Then we have time and by counter both. Yeah, now it will run. 9? What is it? Built-in function object has no attribute. Well, not. It has, just not with us. About now, time. Now it says object has no attribute counter. All right, we'll just import time. That's it. Now, instead of doing all that, it says we have to use sum in Python. Use sum. Python. That's a second implementation. Let's do that. I don't know how, but let's still do that. Now we are doing total, isn't it? Using loop. So instead of doing this, how to just go about doing total is equals to some data. That's right. Total is equals to sum and then data. And now this will be equal to not just by loop, but sum by loop. Time it took is still, yeah, quite comparable. Like, yeah, it looks exact the same, like exactly same. So we need to initialize it. Oh, yeah. So how about just doing it for large data sets? Then we must see some differences, no? How about first 1 million instead of 10 million? Just go about 1 million, just like zeros. Run both. Yeah, it's comparable. Like there is no difference at all. There is no difference at all. First one takes time, second one takes time. See, they both are exactly the same. Like exact. Each digit is exactly the same. So how about now? What is the third implementation? NumPy.sum. All right. We'll use NumPy.sum for doing this. All right. This is the third implementation. We'll code it like this. Total UTL equals to np.sum and then data. As for np, we have to import NumPy. Import NumPy as np. All right. Now we have NumPy. We can do this. Remove this, and we are good to go. Yeah, it took some drastically less seconds for all these. Uh, compare. How about now? Compare. We'll compare all these three. But before that, it's NumPy loop time. NumPy dot np sum loop time. This is SumPy loop time. SumPy seems funny. Paste every variable over here. And py loop time is same. So we'll just copy and paste and remove the sum. This is a py loop, isn't it? Now we'll write print f. We'll have these. Then how about triple, but with f 2 3. Will it be able to run? No. Printf is not defined. Wow. Printf. Oh, sorry. Printf. Damn. Printf. Yeah, it works. Obviously, it works. But before doing all this, So copy and then sort of so it's, you have to do some manual, still some manual work. No worries, we'll do it. Sampy is equal to you also got some suggestions. So let's do it. Delete this and this. Delete it. Delete it. We have this. And above we have this format. Then use this. We say print. Now what? Now what happened? 3 NP and this. NP some loop time is not defined. Yeah, run it all. Now we have a benchmarking, right? Now I see that some also took some less time this moment. Oh no, some was always taking a less time, but we were not paying attention to it. We're just printing this. All right. I was wrong. That's why I was so exact. Like, how could it be? If we run it a second time, it will not be the same. How can it be just two different method but same result? Okay, it was mind-boggling to me. But yeah, here we go. We now copy it. We have implemented our task, which was task one. Use same data for fairness. Is it fair? No, it is not. It is not. Damn it. Do not define n everywhere or just define it single time. Do not define n. Do not define n because we'll run it all together. So no need to define n every time. No need to import time every time so that we know. And no need to create data, isn't it? No need to create data every time. We already have that. Now run all. Yeah, get these data. So what? What the heck? NumPy sum took. Why did it take more time? It's taking more time than this. How is that possible? I'm again instead of printing NP SumPy here. Sum NP sum. Yeah, now it's less. But still, it's quite more. Why? Run all. Do we see? Yeah, it's why is it like that? Seems wrong, but it is not. You know that. C Python is faster than NumPy. Now this is our implementation. NumPy, SumPy, PyLoop. Yeah. Tink, tink, tink. And now we answer our questions. So why is Python loop slower than C loop? Python uses slow. No. Python performs runtime type dispatch. Object handler. Yes. Python cannot use CPU registers not efficiently. Python does not support integer natively. What the? It seems right. B. Now two was the correct answer. Why is sum faster than manual loop? It uses C Python. Where is it? It avoids Python bytecode per iteration. It avoids integer. It converts list into number. B. B seems right. How about question three? Why is NumPy much faster? It uses GPU. Nah. It stores continuously. Yes. It avoids memory entirely. It compiles Python to assembly. Wow. Are you? Oh, damn it. First, your results are suspicious. Yeah, I think so too. Because NumPy sum is taking long time. This incorrect performance ordering. NumPy should not be slower than Python loop. Something is wrong in your benchmarking steps. This is correct. You do not answer them now. So why is your NumPy slow? Most likely you did something like array. No, I did not do this. Array is equals to list np dot random, and then if you pass NumPy list into np sum, NumPy must convert all. Acha. So it seems like our implementation was wrong in NumPy. This is our first code, isn't it? And this is our second code. Then this is our third code. Then this is our fourth code. What I would diagnose precisely. Look carefully that total is equals to NumPy. Data is a Python list. So NumPy must allocate new ND array, copy 1 million elements and convert ints into C int 64. Then perform sum. You are benchmarking, copying plus conversion plus sum, not just the sum. All right. So we must create our own data, which is like uh, np data is equals to np array data. First of all, correct version would be a data list, np array, and then data list, data type. Data type should also be mentioned. D type is equals to np dot 64. All right. Now this seems nice. How about running it all now? Now let's compare it. No. Why no? Built in some. How about just running this code given from ChatGPT directly? Yes, we must look for any errors that might happen. We are doing it before we start benchmarking. So, we are still doing it on data. Sorry. No need for our ChatGPT's copy paste. We can run it all. Let's see the result. What is the result? Yeah, now it seems like it's drastically taking less time. How about this? Yeah, so this is Python loop of writing a solution. OLET by GPT. Solved by GPT. So yes, now we know. copy this, paste it over here, change the Python loop time, sometime, okay, and then numpy time. All right, numpy time, and print it. Remove this or just control it, print it. Hmm. Still, this is like even C Python is losing by quite a lot. Whereas in our code, C Python is not losing by quite a lot. So I guess our implementation is still incorrect, or there might be some flaws that we are overlooking. So let's see. There is data list, which is list range n, which is defined over here. Data list, which is list range n, and then there is data numpy np dot array. Where is that? NumPy data, np dot array, which is using data on data list and is giving us some d type, which is numpy dot int64, and then we are starting ref counter directly with counter. Oh, all right. First implementation is like ours, so no need to check that. All right. Second implementation, which is built in some start and total two, which is again like ours. So total is sum and data list is passed. We are doing this. So I don't think there's a need to check. NumPy sum important already, and the array, which is doing this total three, is sum by np. Yeah, doing the same thing, but still getting difference. Why? There is so much of a difference. Ah, now there is one. Now there's one. Like now it looks fine, and this looks more fine. So I don't know. How about writing everything in a same cell? Will that make something change? Code, writing everything in the same cell. So yeah, implementation second. Second implementation. Say 256 dash 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 implementation 3. Copy it, paste it over here. Implementation 2, and then copy it and paste it over here. Implementation 1. This is common, so we'll keep that separate. This is common, so let's move it upward. All right. Anything else? It's left. Yeah, last printing statement. So let's let's not do something with this. I will just copy it and pasting it over here. printing it all. Will it work? Will there be a drastic difference? Hmm. There is. There is. From earlier, yeah, there is. Your code, my code. Python loops is taking like time, a lot of time. So I guess that's how it should work. Even when our total is like above, start counter, let's move it below. How much difference can it make? How about, oh, it did make some difference, but not something widely placed around. So now we get the point, all right? We get the point. We should delete it, delete this cell, delete this cell, delete this, even delete that. So now we are left with this and solved by GPT. All right. How about just copying it, text, pasting it, and this you get deleted. Yeah, there are too many print statements. Let's just delete this. Okay. And we are all we see good benchmarking stuff. Yeah, now it seems nice. Like both of them are nearly the same. So yes, we can now say we have a great loop. Oh, good. Now this is correct ordering, which is all right. Now speed up is in sum versus loop is 8 to 9 times. Like this is fascinating in itself. Versus numpy versus loop is the drastic difference. Like see 10 to the power minus 2, so 100 times faster. And numpy versus sum is approx 10 to 12% faster. 10 to the power minus 1. Yeah. You still owe an answers. It's not leaving me alone. Third answer. The numpy much faster. Why? Because it element is contiguously typed in. Yes, B. It avoids memory entirely. No. What is fourth? Let us answer this. What is the main cache advantage of contiguous array? Large disk storage? No. Avoid garbage collection? No. Sequential memory fits cache line? Yeah. Reduces thread switching? How about B? Now conceptual explanation required. Explain in 3 to 5 lines. Why did earlier benchmark show 0.5 seconds? Your explanation must include conversions, memory allocations, data copy cost. Be precise. VAR, instead of creating a data specifically in NumPy with the type of int 64 9 npy dot n6 numpy rewrite numpy dot end 64. I just used data list which was an Python object which has uh, Python's overhead, like overhead, like allocating, location. Then what are the others? Memory allocation, conversion to numpy int 64, and then data copy cost. I think this is enough. Good. So MCQ is correct. As for explanation evaluation, your explanation that used Python list, overhead like allocation, conversion to numpy int 64, and data cost copy, this is conceptually correct. Now let me refine it technically. Now you ran something like numpy sum, which is on data, which is Python objects. So numpy internally did what? Allocate new contiguous buffer and converted each Python long object into C's int 64, and which copies value into new memory and then perform optimized C loop. So you benchmark conversion plus copy plus sum. So instead of just doing optimized sum, I did all these. It was lengthy. And now we go deeper like memory layout and system get size of. So we now inspect memory difference. So concept one is, why does system get size of? And what does system get size of actually measures? Get size of gives us the size of the bytes in the file. That's what it gets. It returns the size of the container objects in bytes. Yeah, whatever in the file, uh, it gets the size of the whole file. That is container object in bytes. It does not recursively measure the contained objects. Objects like, let's say there is a container which has all the pointers in the world, but it does not calculate for the you know uh, what do you mean, the data that the pointer points towards. So like pointers are only 8 bytes, let's say, but the data that it points towards is something like 24 bytes. Then we are only getting the 8 bytes while calculating the get size of. Instead, we should be getting 8 bytes plus 24, which is somewhere around 36. 8 plus 4. Yeah, somewhere around 32. 8, 4, 32. Yeah. So that's the discrepancy that happens in, sys get size of. Otherwise, it's all right. It does not recursively measure contained objects. So like if there is a list 1, 2, 3, now Python's gets its size of list, prints the size of list structure, pointers arrays, not the integer inside it. Now each integer is separate object in heap. The concept two is Python list memory model. A Python list is a list object which stores pointers, and then these pointers are sort of pi long, which is a Python data long. So each element is a sort of pointer that's 8 byte, and pi long object is 28 bytes technically. All right, not 24, not 26, 28. And 28 plus 8 makes 36 bytes instead of 32. Now, concept three is that NumPy memory model, which is sort of NumPy array, then NumPy array header, and then contiguous raw data buffer. It's that simple. So if D type is int 64, each element is of 8 bytes and no per element object, no pointer chasing. So memory difference is massive. Your task is to create Python memory inspect.py. So let's create it using text. Python day. Let's say day 5. What is it? Memory inspect.py. MEMO inspect dot by. Now what do we do? We have to do this. We are importing system numpy. We already did this, so why are we doing this again? Let's code it. So import system and then import numpy. I guess our main focus is on Rust, so it's not focusing much on Python, but Python is also important. So we shouldn't be missing out such an opportunity. I've already focused on Rust. I spent approx 3 plus 5 hours on Rust. But unfortunately, all the audio is gone in that video, so I have to just you know record it again. It's a long, lengthy process. Now we have array, which is a numpy array of list, which has now the type of int6, the type of int numpy int64, no? Yeah, has type of np, not int64, which is sort of 8 bytes, isn't it? 64-bit and 8-bit has 1 byte, so 64-bit has 8 bytes. Yeah. Now we print and print and print. That's what we do. Print what? Formatted. So we can directly print. What do we print? System get this get and then size of inside that something. So let's first of all just copy it and paste it multiple times. 3. Anything else? No. All right. So now we use list and then container size. We can print sort of list. All right. Here we have to write, what do we have? NumPy, P is capital. NumPy array object size. So what do we write here is array, which is this array, and after that you're getting array.n bytes, NumPy raw data size. All right, so instead of doing this, we are just getting array dot n b by t s t s bytes raw data size of what? Of NumPy. NUMPY NumPy raw data size. Let's do it. There's an error. What is it? Array and this. I guess this is a data type. Just do this list, and this is data type, right? D type. Then is this. Try it again. Now what? What is it? What is the problem? LST. So type list object is not callable. Yeah, it is not. So what it does is incorrect. Paste it and write out. Ah, we get a error. Can we solve it by ourselves? So it's like getting a data or data list, but you can't call it. So there's no benefit of getting this data. So really, says get size of list, get size of list, array bytes. There's this problem, solve it, Python. Good. This is exactly the kind of mistake we analyze carefully. Another type error. List object is not callable. You try to call something using. I did not. You try to call something like a function using this, but that thing is actually a list object. Python thing list is a list object, but list should be built in a constructor. Therefore, you overrode the name list. What happened? Earlier in your notebook session, you likely did list. Now list no longer refers to the built-in type. Did I do something like that? LST is there. Data list is there. Yeah. So list no longer refers to built-in type, it refers to list instance. List range and becomes which is invalid. Hence error. Now Python name building is fixes either delete list or restart the kernel or rerun this thing. How about just change runtime type to a sort of dview for now, disconnect and delete runtime. uh, we get back. Does it change? It didn't change. Let me change it. I think it was on latest Python 3 Julia. So now shall we run it? Yeah. So we are getting something interesting. We are getting this output, which we'll just take it, paste it. Python resolves name in this order: local scope, enclosing scope, global scope, built in. All right, latest. Get back to CQ. You skipped MCQs. We do not move forward without completing theories. All right. Why did list range fail? Range cannot be converted into list. List was shadowed by a variable. Python cannot allocate a large list. B option is true. B. Now what? Now there is which is the best practice. So either reuse built-in names for convenience or shadow built-ins for to improve performance. Avoid naming variables like list, dict, and structure. Built-ins are protected automatically. Reuse built-in names for convenience. Shadow built-ins to improve performance. Avoid naming variables like this. I'll just say just avoid it. Now the third one is Python name resolution is in order. Oh, local, built-in, and global. Is there any built-in, local, global? This seems all right. Or this is all right. Ah, can I cheat a little? So local, then global, then built-in. So B option would be correct. Local, global, then built-in. Wait, good. Everything seems correct. Now value is correct. N is sort of 1 million. 1 million, no? Yeah. Now the critical insight is these numbers are misleading if interpreted shallowly. Shallowly. Yeah, shallow. Seems weird to speak shallowly. Shallowly. Well, still. Now, the system get size of a list does not include the memory of the integer. It only includes the list object header. Now, the internal dynamic array of pointer is like each pointer is 8 bytes, and there are these many pointers, which is these many bytes. 1 million pointers, which is 8 million bytes. Now, which matches your 8 MB? What about the integers? Each integer is 28 bytes, implementation dependent, and 1 billion integers is 28 bytes. So actually, yeah, I know it, 36 MB total. Now, the Python memory, NumPy memory is something like 8 byte per element. So it becomes for the whole 1 million, there are only 8 MBs, no separate objects. So total is 8 MB plus small header that is about 112 bytes. But if we see the raw data size, it is exact 8 MB. Now the list is approx 36 MB, NumPy is exactly 8 MB, which is 4.5 times more memory efficient. Now this is huge because this list gets loaded into memory and then we do stuff with it. So if memory is more free, we can utilize it more efficiently. If memory is loaded, well, it will start to get sticky over there. Now we go hardware level. So hardware level is the concept CPU cache line. So typical cache line is 64 bytes, and for integer 64 arrays, there is 64 divided by 8, which is 8 elements per cache line. So one memory fetch loads 8 numbers, or 5 for Python list cache line loads 8 pointers. Then CPU must follow each pointers. Now loads separate by long object, likely another cache miss, and this is pointer chasing. Now memory latency dominates. Theory one is why doesn't system get size of low list shows full memory usage. It hides memory. Now it measures container, not reference objects. Yes, Python compresses it round numbers. So B is right. Second, what is it? Approximate memory per Python integer is approximate memory per Python integer is how much? Per Python integer is 16 to 28 bytes. Yeah, 28, and then pointer is 8 bytes, so it makes it 36. So it is C. Why does pointer chasing reduces performance? Obviously it does, because it is also taking some sort of performance issues and has some overload to it. It increases arithmetic cost. Yes. It causes additional memory fetches and cache misses. Yes. So B seems more appropriate to me. Now the fourth question, which is for 64 byte cache line, 8 byte integers, how many elements load per fetch? For 64 byte cache line and 8 byte integers, 64 byte cache line and 8 byte integers, how many elements load per fetch? 8 elements? Easy, easy, easy. B. A short written test. Oh my. Written test. It always catches you off guard. Now 6 to 8 precise lines. Explain why NumPy enables SIMD. What is it? Single input, multiple, something like that. Huh? SWT. 1. NP enables SIMD because in a single day it does multiple calculations. Uh, PARALLY parallelly. Since I've forgotten, what SIMD means. It's something starting with single and then multiple or single and multiple. Yeah, two dot. Why Python list cannot benefit from SIMD easily? Sort of single fetch because Python STO parallel as the data are con what is it conjugate is different conglomerated no data is conjun con consecutive consecutively arranged conjoint. Was it conjoint? So let's write conjoint. I don't think it was conjoint. It was let's say consecutive. Consecutive. Is it correct? Parallel calculation. Single, not slingle. Uh-huh. Single. Because Python stores pointers side by side, and then they have to be dereferenced to get to the actual integer, and then to be arithmetic on it. I guess this seems right. A third, why memory bandwidth often limits performance more than arithmetic? Why does it? Memory bandwidth, like memory speed or the speed of our RAM, because of the fetches and the Python overhead, because of the FETCHES fetches of the integer and data memory overheads and integer data and memory overheads and what this integer data and memory overhead. Oh, I forgot. BC because of fetches of the integer integer and data, MEM, memory overheads, HE, and large file, large data size. Good. MCQs are correct. Conceptual base is solid. As for evaluation of your explanation, SIMD because in single take it does multiple calculation per correct direction but imprecise. SIMD because data is stored contiguously. See, this is the word, and you don't remember the word, and this whole answer goes to some sort of shithole. And then data is stored contiguously in homogeneous typed buffers. You know that 8 bits, 8 bytes, 8 bytes, 8 bytes, contiguously. Now, compilers generate C loop can never use vector instructions like AVX. Compiler generated C loops can use vector instructions like AVX. So SIMD registers operate on multiple adjacent values per instruction. And this requires predictable, aligned, contiguous memory layout. SIMD does not mean parallel in general. It means vectorized instruction level parallelism. A Python list limitation is you said Python stores pointers side by side and then they have to be dereferenced, correct? But precise version would be that Python stores the pointers to boxed pylon objects and then each pylon objects live elsewhere in heap memory. Now SIMD requires raw numeric buffers and then Python objects include like metadata and not laid out as plain numbers, and therefore compiler cannot treat them as vectorizable numeric array. All right. So now memory bandwidth limitation. You said because of the fetches, overhead, refined version would be modern CPUs can execute billions of arithmetic operations per second. But the DRAM latency, which is 100 nanoseconds, and CPU instruction latency, which is less than 1 nanosecond. So if each operation requires new memory fetches, CPU stalls waiting for memory, and thus performance becomes memory bound, not compute bound. You understand this correctly, right? Now, final test before we move to Rust. Analyze these carefully. First is arithmetic. It's extremely fast, but memory is slow, so performance becomes. Arithmetic is extremely fast, but memory is slow, so performance becomes memory bound, not CPU bound. All right. So it is memory bound, not CPU bound. Which structure is more likely to saturate memory bandwidth? Is it linked list? Yeah, I guess. Python list of objects? Continue? No, never. Dictionary. Linked list is sort of a data structure that is faster, I guess, than some of the dictionaries. Or is it not? But Python list objects is something that has more than just list to it. It has objects, it has to allocate memory, it has to then dereference everything. It has linked list is also something like that. But Python has more overhead. That's what we know. And third one, linked list was also implemented in sort of C, so it's faster. So yeah, if the linked list was implemented in Python, then yes, it would have more overhead than this, but it does not indicate it is implemented in Python, so we'll not take it. We don't assume anything, right? The third one is why does some list not use, because it's written in C Python, not use SIMD automatically. C Python doesn't support. Python integers are boxed objects, so sum is slow. Python disables factorization. C Python doesn't support SIMD. Seems like right way to go, but Python integers are boxed objects. Can that be a reason to right thinking? Oh, there was one more question. You must process 1 billion flows, which is far better. Python list of floats or numpy? Always this. Ah, we have to answer in 4 to 6 line. All right. MCU, this is correct. This is incorrect. Why? Contiguous numeric array can saturate memory bandwidth. Oh, there was one more options. So, this is. So it says contiguous numeric array. Seems nice. Like it is contiguous and it is numeric, so it is also array. Which structure is more likely to saturate memory bandwidth? You guys said B, but it was wrong. Why? Contiguous numeric array can saturate memory bandwidth because it streams data sequentially. CPU pre-fetches data predictable and access patterns, so it can continuously pull catch lines at maximum throughput. And Python list of object is slower due to pointer chasing the cache and misses, so it rarely reaches the full bandwidth efficiency. So the structure that most effectively and stress memory bandwidth is a contiguous array. Was it about using memory bandwidth? Which structure is more likely to saturate memory bandwidth? Like use efficiently. Contiguous array will use it efficiently. I didn't understand that question. I thought which will slow this memory bandwidth. Now, your answer for this one, A or B, B is correct. C Python can use SIMD internally in some operations, but some list cannot because list is a Python object. So cannot because SIMD, because Python integers are boxed pylon objects. They are not stored as raw contiguous numeric memory. SIMD requires raw primitive buffers. So the limitation is object representation and not lack of SIMD support. A conceptual correction summary is that memory bound systems are limited by RAM, latency, or bandwidth. A contiguous array maximizes bandwidth utilization, and SIMD requires raw homogeneous data. Python object block spectrization, and now answer the applied question you skipped. Oh, I skipped. Yeah, I did. Which one is better? NumPy Float 64 is better. Why? Because it has no Python overhead. It is implemented directly in C as float with 64-bit of memory. So 8, 8 na? There are 64 bits. How many bytes are there? 8 8s are 64. Yeah, 8 bytes. 8 byte for one data point. For one data point, which when compared to 8 byte pointer plus the 28 byte pylon is far more efficient and fast. Code 64 array. NumPy also keeps those data consecutively. Array, what was that word? Congruent. Shit. Uh, Contiguously. Sorry. Contiguously. Giusly. Conti. There's no conti. contiguously. So better at CPU, HACHING. Answer in 4 to 6. You must include memory layout, cache behavior, SIMD possible. Yeah, SIMD is possible in NumPy. What else? Object override, I did, and no vague wordings. No vague wordings. It's totally to the point. Good. Direction is defined. Now I refined to system grade clarity. What is it? Final evaluation is that applied answer. Your core points are correct. No Python object, 8 bytes per element, contiguous memory, assignment possible. Now I restate it precisely. For 1 billion floats, a Python list stores 1 billion pointers, 8 byte, and Python object is approx 24 to 28 bytes each. That's what I said. Now that is 32, 36 GB of memory footprint, catastrophic. Whereas NumPy has total 8 GB contiguously. And also, contiguous memory enables cache efficient streaming and SIMD vectorization. That's what I said. Again, a Python list requires pointer chasing and boxed object arithmetic. NumPy executes in compiled C loop. That's what I said. And possible vector instruction. I did not use this vector, and vectorization. So I guess that's right. Let's add to the proportion. But therefore, NumPy is both memory efficient and bandwidth efficient. Your reasoning is fundamentally correct. Day5 is complete. Uh, but for the past two, 2 days, we were doing the same thing. So when will I I I learn something new? कुछ तो नया सीखा भाई. You are not doing the same thing. Control flow semantics, Day5 Python, uh, Rust. You are about to understand zero cost abstraction binary upload. I was talking about Python that we are covering for the past three 3 to 5 days because I skipped some of the days now. Then I had to cover on day 5 or day 2 or day 3. Good. Let's address this directly and precisely. You are correct in observing the repetition in the theme level, but what changed each day was abstraction depth, not the topic level. Let me break it down. So day one was you're thinking in terms of system, syntax, loops, and basic performance comparison, surface level performance curiosity. Day three was something like you began touching C Python internals. I didn't. I didn't. I C loops beats in theoretical, yes. And bytecode versus native code. And shift was language level to runtime level. Now, day four, you explored object representation, pi long memory cost, and pointer chasing. So, runtime level, memory model, and day five moved into cache line behavior, SIMD constraints, and memory bound versus compute bound. Now, bandwidth saturation and shift is memory model, that is hardware level reasoning. It feels repetitive because the domain is still performance, but the mental model is expanding downwards. Language, interpreter, object layout, memory layout, CPU architecture. This is the progression. Now, here is the important part. Python has very little left at this abstraction layer. You now understand NumPy is fast, Python loops are slow, where overhead lives, how memory layout affects performance. Now, this is already beyond 95% of Python. Python developers. All right. So yes, we are done with deep Python system fundamentals for now. From here onward, Python will be used for ML level abstraction and Rust will be used for system level control. If you want something new, different in Python next time, option includes GIL internals and threading models. Yeah, this seems nice. What is GIL? General library. What is it, GIL? Multiprocessing versus threading architecture, C Python reference counting, that is plus GC, writing a small C extension. I don't want to get into C. No, no, no C. Use Rust. NumPy broadcasting internals. Uh, but today's Python system modules is complete, and we escalate into Rust dynamic dispatch, which is entirely different territory. So I ask you directly: do you want to continue Rust trait objects, deep dive into GIL concurrency model, something? Choose direction. Uh, what is the day or point when we start combining Python and Rust, both for our ML and data science? Excellent. Now we are asking the right architectural question. You don't combine Python and Rust randomly. Combine them when Python becomes orchestration and Rust becomes compute core. Now that transition happens after you understood both sides deeply enough. Let me structure this clearly. The real integration point, you combine them when you can answer what parts of ML is compute heavy. All right. What part is glue or orchestration? What part needs memory control? What part benefits zero cost abstraction? You are close, but not fully there. Timeline is realistic architecture plan. That is phase one, language mastery. Now, current phase is goal, Rust ownership, traits, lifetime modules, error handling, performance reasoning. And Python is NumPy, internals, memory models, performance limits. We are still finishing this. Phase two will be Rust compute core, which is next 7 to 10 days. You build matrix structure in Rust, trade based, trace, trade-based operations, generic numeric abstractions, and error propagation. Simple linear algebra engine. And now you have a system compute core. For phase three, we have FFI bridge integration phase. This is when Python plus Rust meet. We use PYO3 and Maturin. You expose Rust function as Python modules. Example like import Rust linear and Rust linear dot mat multiplication for matmul, and then we pass AB. Now Python becomes data loading, model structuring, experimentation. Rust becomes the hot path math engine. Real answer to your question is we begin combining them around day 12 to day 15. So how much days left? 10 days. Oh my. And not before. Why? Because if you combine early, you won't understand where the overhead lives. You won't design the Rust side correctly. You'll treat Rust as faster Python, which is wrong. Now, what integration looks like? Example architecture is like Python has dataset loading, model training loop, and loss function logic. Whereas Rust is matrix multiply, convolution kernel, optimizer step, and memory buffer management. This is how PyTorch is built. So we can just use PyTorch now. What Python API. So C++ and CUDA backend. We are recreating that mental model with Rust. All right. Another important question for you. Why not just use NumPy everywhere? If NumPy is already passed, why would we need Rust in machine learning? Think architecturally. Answer in 4 to 6 lines. Be precise. I don't know. After that, I'll show you the roadmap to integration. Why do we use NumPy? Uh, I guess for customizations. I this to build customization and learn from building custom engines, algebra or matrix vector if possible, contribute to open source libraries. Good instinct, but that answer is incomplete and still naive. Well, what would you expect from me? Customization and open source contribution are side benefits, but that is not the real reason. Let's think architecturally. NumPy is extremely optimized, written in C, uses BLAS under the hood, and already SIMD aware. Now already cache optimized. So if performance is only goal, why introduce Rust? The real reason Rust enters machine learning system is here are real architecture drivers like memory control. In the large machine learning systems, you need custom allocator. You manage large buffers. You control lifetime precisely. You avoid unnecessary copies. Python cannot give you that control. And zero cost abstraction. You may want trait-based tensor backends and pluggable devices like CPU or GPU. Now, generic numeric type. And Rust gives compile time abstraction without runtime overhead. All right, safety at scale. So C++ and C backend are sometimes undefined behavior risk. Rust backend has no data races, no use after pre. Memory safely guarantees for production like ML infra. This is huge. And system integration in the real machine learning system, networking, storage, async, streaming, and model serving, inferences engines. The Rust excels at system level orchestration with safety. Python does not. Another deployment constraint is sometimes you need small binaries and no Python runtime. Edge devices like WebAssembly targets. Sometimes you need small binaries, no Python runtime. Edge devices like WebAssembly targets, and Rust can compile to static binaries. NumPy cannot. Now I ask you properly, if you were designing a high performance based inference server, where would you put HTTP handling? Browser handles it. I don't know. Python or Rust? Rust would do it. Tensor math, obviously Rust. Model loading, Python. Request orchestration, Python. Copy this, paste it over here. HTTP. It's WebAssembly now, so we'll use Rust. Tensor maths, we'll write, WebAssembly. As for your tensor maths, what we'll do is use Rust. Model loading, Python. Orchestration, Python. What else? Good. Now we refine this architecture. You answer this Python, Python, Rust, Rust. This is directly correct but incomplete. Let's analyze component by component, like system architectures. All right. Now, HTTP layers, you said Rust, which is WebAssembly. Correction is that server side, which is Rust, has Exum or Xatix. If browser, then WebAssembly target. And if Edge, what is Edge? All right, if Edge, Rust static library. Now, the correct reasoning would be HTTP handling benefits from async runtime, low latency, concurrency safely, and no GIL. Rust is superior here. But we are not industry level expert at writing, so we are not superior. So that's a drawback. Now the tensor math, you said Rust, correct. Hot path must be SIMD optimized, possibly GPU accelerated, and memory managed precisely. Now this is backend territory. We don't even have a GPU. How about possibly accelerating it? Model loading using Python depends. For research workflow, Python loads model definitions like py.style, and for production, Rust loads serialized weights. Python not required at runtime. So real architecture is training phase for Python, inference phase is for Rust. Now, important distinction is orchestration. Use it Python. Now, the research experiments, yes, but for production inference servers, we use Rust. Why? Because GIL limits concurrency. Python multiprocessing is heavy. Rust async is far more scalable. And now here's the real architecture pattern. During the training, the Python has data pipeline, model experimentation, logging, visualization, whereas Rust has custom kernels, which is optional, then performance critical extensions. And during production inferences, Rust can use an HTTP server, model loading, tensor execution, so memory buffers, concurrency. It means everything. And Python, well, possibly not present at all. Very good. What the heck? How did this chat shooting become like this? Like, Python possibly not present at all. And we are learning Python. Well, we need to understand now somewhere how everything happens system level. Now we define integration point. You ask, when do we combine them? We combine them when you can build minimal tensor engine in Rust. Then we expose it to Python via PYO3, and then this will happen around day 12 to day 15. Before that, Rust fundamentals must be rock solid. Traits, lifetimes, error propagation, module architecture, ownership across abstraction boundaries. Without that, integration becomes chaos. Now I test your architectural thinking. Suppose you need 10,000 inferences request per second, which is the bottleneck in Python. Now, arithmetic speed, I don't think so. GIL connections, probably. NumPy internal speed, never. Disk operation, input output, no. So I think GIL might be the culprit behind this. B, GIL. Choose one and explain in 3-4 precise line. GIL contention. Contention. What is bottleneck in Python? Which is the bottleneck in Python? NumPy is written in C. So sort of fastest because of optimizations like SIMD, contingency, etc. Arithmetic speed is controlled by CPU, which is fastest of all. So if you can write WebAssembly, well and good. Disk I/O, well, SSDs are fast, so no. And GIL, I don't know about that. Good direction is correct. Now we sharpen it to production grade precision. Why? GIL contention. Why? In high QPS inference servers, so request arrives concurrently, and Python threads cannot execute Python bytecode in parallel due to the GIL. Even if NumPy releases the GIL during heavy C computation, request orchestration, parsing, and post-processing still requires Python level execution. Now the bottleneck becomes thread serialization around the interpreter. So the system become concurrency bound, not arithmetic bound. Important nuances: you understand arithmetic speed is controlled by CPU, which is fastest. But this is incomplete. Arithmetic is fast, yes, but in real inference systems, memory access, serialization, deserialization, scheduling, and synchronization often dominates. So the GIL amplifies that constraint. Now we clarify the strategic insight. NumPy is fastest for single large tensor operation, but inferences server often involve in many small request concurrent execution, network input output, request routing, memory management. This is where Rust shines. A critical question. If NumPy releases GIL during heavy C computation, which Python is still which is Python still not ideally for high concurrency inference servers? You think carefully. Your answer must mention non-NumPy based. Aha. So shall we start to polish our Rust basic concept and increase the base? We must build build something real today. Start की spelling error, polish की spelling error. Now that instantly is correct. Now we accelerate to Rust. All right, let's end this day 5 IPL, whatever that was. Where is it? We are not building. We do not build randomly. We build something that forces state versus dynamic dispatch, object safety, and module structuring, unit testing, architectural thinking. Today, build a pluggable compute engine, mini ML core. This is not Troy code. This is architecture training. So, goal today is to build. I think we have to use some, you know, I'll have to use cargo. You will implement static dispatch and implement dynamic dispatch, store heterogeneous operation in vector box, which is then dynamic operation, which has dynamic operations, and then benchmark static versus dynamic, add test. Now this is real system engineering. Step one is concept first. Before coding, you must understand static dispatch, that is generic. Today's day 5 now. So shall we go to Rust back again? Dun, dun, Rust 05 ls, and we remove all these. This is like these all 8.rs are all the files that I sort of made during, Rust by example live stream. But unfortunately, we do not have the audio. We lost it. We do not record it. So yeah, both of those live streams are just without any audio. Now we create step one is that static dispatch generic. Before coding, you must understand concept first. All right. So static dispatch, which is generic. So fn, there is function execute, which has a t vector or t. What is this? T operations. Seems like a vector, and the type is operation. And then we are passing operation T, then passing A, which is F64, B, which is F64, and we are returning F64. Operation is something like add, subtract, something like that. Now compiler generates execute, add, execute, multiply. No runtime cost, binary is large. All right. Now the dynamic dispatch, which is dyn. Now what it does is executes the operation A and B, but instead of taking this static operation T, We are taking a dynamic operation. Yeah. Now what is this? This is a fact pointer. V-table lookup, indirect call, smaller binary, slight runtime overhead, but test theory before coding. Mono monomorphization, 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 monomorphization increases runtime speed, binary size, memory allocation, and heap usage. Since it is single, it speeds up, or it has lots of size, or it has memory allocation, heap usage. Not heap usage, no. Memory allocation, so it's single. How much memory can it use? Binary size, yes, everything is in binary. Runtime speed is good, I guess. Question 1A. Why can't we write FN execute and dynamic operation? Dynamic is unsafe, dynamic is unsized, dynamic must be mutable, dynamic is deprecated. Dynamic is mutable, I guess, or dynamic is unsized. So 2B, dynamic is unsized, which allows the heterogeneous types in vectors. Operation, dynamic. Yeah, please see. Dynamic dispatch costs come from heap allocation, indirect function pointer call, or trait definition, which is ball checker. Dynamic dispatch costs come from heap allocation. All right. Indirect function pointer call, trait definition, or ball checker. I guess it would allocate on heap, so slight overhead. But indirect function pointer call is also might also be the reason. Indirect function pointer call. A or B? I will choose A. Answer these. After that, we start coding. Today we built real architecture. Today we will create program using what is it? Cargo. So if those commands as well as give file names also. FILE file names also. Good. You want to build with cargo properly. This is correct discipline. But first, your theory answers are partially wrong. I know that. We do not go code until theory is correct. All right, let's correct it. So MCQ first. You answered A. Correct is B. Monomorphization increases binary size. Yes, it does. But where is it written? It also increases the speed, no? It is also speedy, so I guess increases binary size. Why? Because compiler generates a separate version of the function for each concrete type. It does not inherently increases the runtime speed, but removes the dynamic dispatch overhead. But that's different. Now, this is correct. That correct is dynamic trait is unsized. And 3 is also correct, which is a dynamic operation is there, which allows heterogeneous types. And then fourth is I answered A, but it should be B because dynamic dispatch cost comes from loading vtable and indirect function calls. Now, what is vtable? Is it virtual table? But what is it used for? And heap allocation is not required. You can use ampersand dynamic trait without heap allocation. You can use ampersand dynamic trait without heap allocation. All right. So that seems like a plus to me. You must correct understand. Explain 3 4 line why monomorphization increases binary size. Why does that? Monomorphization. Everything is compiled into binary, but in dynamic it has to create v tables and what? I know I am answering it wrong, but I still want to write what I can think of. V tables and where was that? Because compiler generates separate version for a function for each concrete type. Does not increases runtime, but the dynamic dispatch overhead is different. V table pointer call and indirect function call. V table pointer and uh, indirect function call. Ah, I didn't answer the second one. Oh, sorry. Why dynamic why dynamic dispatch does not necessarily require heap allocation? Why? Because dynamic dispatch override. Because you can use ampersand dynamic trait without heap allocation. Incomplete and partially confused. You mixed my dynamic dispatch into answer. We fix this cleanly. That's what I want. All right. So we left it there. So concept one is why monomorphization increases binary size. So when you write something like execute and then T operation, where operation is type T, uh, then the compiler generates a separate concrete version of execute for every T used. If you use add multiply, you now have a execute add and execute multiply. Compiler generates separate concrete version of execute for every T used. So if we have operations like add and multiply, we have execute add and execute multiply. Each version is compiled into machine code. And the more concrete types, the more generated function, so large binary. Now this is compile time duplication. No v tables involved here. Correct concept two. Why dynamic dispatch does not require heap allocation? Because uh, dynamic dispatch requires a fat pointer and indirect call through vtable. Heap allocation is only required if you use box and dynamic trait. All right. So again, why dynamic dispatch does not require heap allocation? Dynamic dispatch requires a fat pointer which is data pointer plus vtable pointer. So data pointer plus vtable pointer. And the second one is indirect call through vtables. So heap allocation is only required if you use box and dynamic trait, but you can use what? Ampersand dynamic trait without box. I don't know how that works. Which is borrowed reference, no heap allocation, and still dynamic dispatch. So dynamic dispatch is not equals to heap allocation. Heap is optional. Now you restate correctly in your words why monomorphization increases binary size, while monomorphization every every PV every operations in the execute gets formed again like the execute add and and execute, let's say, multiply, which is compiled and added to your binary separely separately. sepa sepa separately, yeah. So that increases the binary size. Now the second one is, this was first one. Now we have second one, which is why dynamic dispatch does not automatically imply heap usage. Dynamic dispatch require a fat pointer, which is data pointer pointer and readable pointer, and it does not automatically means, and it means that it requires the key, but something like operation into that, you know, ampersand dynamic OP has to use key, but that doesn't imply that automatic imply heap usage. Better now. I now correct your precision, monomorphization, correct. Explanation is correct. Generate function is duplicated per concrete type. Each version is compiled separately. That duplication increases binary size. A small correction is needed. You wrote something like operation ampersand dynamic operation has to use heap. That is incorrect. Dynamic operation does not use heap. All right. Ampersand dynamic trait does not use heap. This does not use heap. That's what it's telling me. Operation is just the reference. So no heap allocation. and the underlying object could be stacked allocated. Stack allocated. The heap allocation happens only when you explicitly use acha dynamic, no address, no reference, just directly dynamic. Because now box allocates on heap. Dynamic dispatch and heap allocations are independent concept. Now we conceptually now your conceptual foundation is solid. We proceed. Step one is we create the project, not day five, but let's do it anyways. So we use cargo, and then new Rust RUS3 Day5. All right, we have something. What do we have? We have source, we have main RS, we have cargo.toml. Now, step two, create file structure. So inside SRC. So go inside, first of all, Rust, and then go inside SRC. All right, we have main.rs, but we only need operation, then traits.rs, then operation mod.rs, operation add.rs, operations multiply.rs. Let's do that inside SRC. We'll make directory called operation. Then we'll touch these. Oh, what did happen? Let's ls. Yeah, let's do three. Operation add multiply this, that. All right. Final structure is something like this. Concept first, design later. Let's first of all tree this whole damn thing. This and this. Will we get what we expect? Now, we only need this. Hmm. This is a file tree. Copy it, paste it over here. String. Now we are defining traits. So we use pub. Earlier we did not use pub. Pub I guess means public. And this was the same like trait and operation. And then inside that trait we are writing something like function called compute. And then we are computing this. We are not creating the whole damn thing because function is not ready, but this is a trait. All right. Inside the operation add rs. All right, we use vim for this also because new vim we have exhausted something called credits in new vim for intrates.rs. All right, intrates.rs, we go like insert, we go like public. Inside that we have to create traits or trait, right? Then operation. Inside that we have to use curly braces, right? Then we are creating something called function of type compute, comput, compute, not computer, compute, which takes first of all self, and after that it takes, you know what, a, which is of type f64, I know, yes, and then it takes b, which is again of type f64. That's it. We'll get f64 also. We also sort of get f64 from this function, and we end it. We do not return this thing. We don't return anything from trait, right? Now, inside operation, we add rs, all right. Let's first of all save this. Uh, then we go to, explore inside operation, inside add.rs. We use something called use create and then trade inside that operation. All right. So we are saying use, right, just insert, and we are saying use, then we have a create. I don't understand create yet, but let's do it. Create, inside that we have a trade. We have a trade. And inside that we have a operation. 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 All right. Do we use semicolon? Yeah, we did use semicolon. So we'll go back, not like this, not like this. We'll append, use semicolon, create next. Now what? We'll say public and we'll add a structure called add. All right. There will be a structure called add. Nice. Public struct add. Publ. Yeah, not public. Pub. Struct struct add. This is correct. Add. This is it. Why is it indexing? What is it doing? Layer std. All right. Something happened in my Vim also. Now we'll implement operation for add, and here we'll say that this will compute. This will compute a and b and will give us result a plus b. All right. So we'll implement the operation over here. Operation. How do we get it here? How do we get it? Opera. Operation. Operation. Syntax error. Expected this. Yeah, I know. Operation. Implement operation for. For add. Then we do this. Isn't it? Yes. So go to the what is it called? And back. Insert. Let's keep it back for formatting. And here we'll define something called calculate, CALCULATE or compute. COMPUT. Yes, because compute is a trait in operation. So we'll define compute. Inside that compute, we will pass on the same things that we passed in trait, which is first of all self. Then we'll pass a, which is of type F64. Then we'll type b, which is of type again F64. Then we'll close this and it will give us a result which is also of type F64. And then we implement the damn thing, which is a plus b. This is it, isn't it? Same. Operation add, use create, CRATE, trait, not. All right, traits. Let me see. I used here trait, and we have to use traits, which is our file name. All right. Therefore, we are seeing something like red over here, and it is underlined. So I guess not this. Use traits. Now this is different color. Is it? Now that red gets blue. Nice. Now we implemented operation for add. Then we created a function which takes self a b and gives us F64 a plus b. Am I ready to go? Operation. Yes, I guess. Then we'll implement the same thing for, you know who, Explorer. I'll say multiply. File is not included in any crate, so Rust Analyzer cannot offer IDE service. Let me include it in a crate. So we'll say use same crate, crate, and we'll say, you know, traits, which is USB T array ITS. There it says something like, P or something, so that I can accept. I am not able to accept this. Inside that, operation. That's it. Now I will implement. That's what going to happen now. If not, then we'll change it. Implement what? Implement operation for mul, mul, mule, or capital mul. What is it? First of all, this decide this. It is multiply, not mul or mul. It's multiply. An operation for multiply. Good. So we publicly define as stru, struct, struct, publicly struct called capital M. Yeah. Multiply. 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 Yeah. Hmm. Multiply. Or multiply. All right. We'll go like this. We'll create another function. No, the same function, which is compute. We'll pass on self like this. And then we'll pass a, which is of type f64. Why don't we just copy it? No? And there's b, which is again f64. But if we want to copy and paste it, then we can just do it using ChatGPT also. It's also giving us something, no? But we don't want to do it. We want to write by our own hands so that we can feel proud of ourselves. Now we'll pass on a multiply b. It is a return value, so no semicolon. Let's do one more thing. Uh, Insert enter. That's it. This is it. In operation mod, what is operation mod? We publicly say pub mod add, pub mod multiply, pub use add, pub use multiply. What the hell is this? But all these adds and multiply are capital, and here it is small. Why is it? What is the reason behind this? I don't know. But now it says, so we'll do it. So we go to execute, we go into mod, we go over here, we say pub mod addition, isn't it? No, it says add. Wow. Then it says pub mod mul. No, it says multiply. Wow. Then it says pub use add. Pub use add, which will use add. Pub use, oh, double colon. Pub use add. Then we have pub use multiply and multiply. This re-exports for cleaner use. This re-expose for cleaner use. All right, I'll take your word for that. All right, let's save it. Not here. We'll just save it. I didn't add something. That's why it was this. I'll go like, oh, I guess there is no error with this. We'll save it and then we'll go like explore and back. You'll say main.rs. Where are you? Delete this damn thing. Open up a new line. Now we implement both dispatch types. Static dispatch using execute static, and then we say dynamic dispatch using this, and then heterogeneous vector is there, which is this. Now implementation task. Write all files manually, make sure it compiles and run this. Print result of static add, static multiply, dynamic vector execution. What the hell? Why does vector dynamic operation not compile? Does not compile. And box dynamic compiles. I don't know. What would happen if compute returned self? What would happen? Nothing. Because compute's task is to, calculate or compute something. If it's returning self, it shouldn't, at the first place, it shouldn't be returned because the return value can be f64. And I don't think self is f64. So let's not think about what would happen because before that happens, we'll get an error. Do not skip it. Build it. Then paste your main.rs. Before doing this, you have to create another operations. Okay. Documentations. How to use these documentations? I can't touch it. I can't do anything with this. Use std hash, use core hash, std hint. By that fits how core. Now what we have to define is, first of all, these three things. Let's say static dispatches, this execute static and then static operation. When execute static, static, and inside that we have operation t, which has type p e array operation. Close it, and then we pass something like, what do we pass? We pass op, that is t, and then we pass a, that is again f64. That's what we are doing now. Yeah. B, that is again f64, and then the result will be of type back again f64. implement function tab. What we do compute and then pass the a and b to the compute module, and it computes according to the operation that was determined or defined. We say operation dot compute. Okay, sorry. We say op not compute instead of just compute. Is that all right? Seems so. Now we we'll just do this or this, and then we'll say a function called execute, cute, execute dynamic. Inside that we have a t, not t. We should have an ampersand. Dynamic operation. It is like this, not this static one. We have a ampersand dynamic. Okay, OP is type of ampersand dynamic dy dynamic. Dynamic what? Dynamic operation. I dynamic operation. Then we send A, B, and then compute. Simple. It's same. Not very same, but yeah, we get the point. F64. And then B is also F64. And we say so F64, which again does OP dot COMPUTE, and it also passes A comma B. That's it. Then we close this bracket. We should come to the next line before doing so. And yeah, now heterogeneous vector. So now there is OPS, operations. Then there is vector box, which is dynamic operation, which is a vector not equal to box add, box new multiply. All right. So let vector, let ops. Let ops is of type vector. Yeah, yeah, is of type vector, which is I can't take it. So vector has box and dynamic operation. Vector has box and dynamic, not this, dyn, dyn operations, operations, close, dynamic operations, and vector is vector not equal to this. Is there something wrong? Because I am getting different sort of colors for operations. All right, seems right. And we have a square bracket. Then we sort of end that square bracket with a semicolon. Then press enter 2 3 times. Then what do we do? We create box new add, box new multiply. Double colons. We say box. We say new add, and then we say box new. Do we use semicolon or not? Do we have to return this? Multiply. Seems like right. Use comma. Right. Use comma. No semicolon for now. Now, what is inside this main function? Since this is our first time doing something like that, so I don't know. Write all files manually. Make sure it compiles. How will I make sure it compiles? I'll just paste it back to you. How will I paste it back? I see some errors. I see some real life errors happening right now. Is equals to vec. Small v. All right, all right, all right. We'll come to line 11. More down. J. Word. Replace with small v. I don't think there is error now. Or is there? I think there is still error. We don't know, we don't care. Whatever the case is. Vector, box, add, box, multiply, everything seems right. Yeah, but I still am getting this spooky red line. Can I know the reason, mister? Can I know the reason? Why it is syntax error? Expected an item. What item here? I don't know. This is my first time doing all this. That's what everything. We'll just WL copy cat operation is. Does it matter if operation is whatever? We'll try pasting it. Yeah, it got pasted with main and public trait, which is a different thing altogether. Inside operation, do everything, copied everything, we paste everything. Now, please guide for word. Because I haven't even sort of streaming interrupted, waiting for complete message. What the hell? Did I not just completed the message? Chat GPT can also show us some errors. That seems new to me. We were in middle of dust dispatch, so no drift, no resets. Created cargo project and file structure. Now continue. Uh, Have you run cargo new Rust 5, created operation folder, added trades.rs? If yes, paste your current main.rs. If not, say where you are stuck. Can I get a command that works like trees but can also read files with name like cat star wl copy but better VEDDR more ADVANCD more advanced because I need that so that I can copy and paste. Yes, you want something like shows directly like tree, includes file name, optionally prints the file content, can pipe to clipboard, more power to them. You want developer grading tooling. Option one is EXA, which is modern tree replacement. Level 3, and with that, let's get does not print file content through just structures. Option 2, BAT, advanced file printing. Find files. Print all Rust files with syntax highlighting and pipe it to clipboard. So I guess it's nice and much better than cat. Option 3, whole project dump structure if you want directory and everything. Tree, then echo, and then there's find type f, name rs, print exec cat, wl copy. Better formatted version is this. So option 4, professional rip grep plus formatting. Install rip grep. Best practices for development, use exa for tree view or WAD for file reading. Just make this executable and move it to some binary so we can use it anywhere, because this seems like a nice idea. And for now, let's try just running it and paste it over here. Create a string script, uh, proj dump, pdump, all right? Not proj dump, pdump. Is there any program called pdump? If there is not, there will be. PDF, no PDF. I want pdump, dump. So we'll create this where? Create this script. Vim, we'll create this at pdump. Seems like nice. Then there we paste this. Yay. Project dump to clipboard. This seems nice. And then save and exit. Yes, we will do it. Save and exit. What we'll do is now ls-l, go there, p dump. We'll check for the permission. It is not executable. So we'll say chmod plus x, make it executable. Make what? Make p dump. Seems like a nice name. P-dump. Right. All right. As soon as we do the P-dump, project, make directory P local bin. Option 3, move to global binary location. Be local bin and move project dump to local bin. Make sure local bin is in path. If not, add it, reload and sudo system wide. This seems like nice. I use anyway. It will print all RS file content. Before doing that, I want to ask some questions. Will it work like this? Be dumb, let's say this, and then this, or this, like this, on relative direct PORIES, and we have to pass on the path. If it says yes, I'll just make it. Nah, the current script will not work directly for pdump and this because it ignores positional argument, always uses this. Fix this properly. Pdump this, then it will do this. If it is, then it will do this. If it's some absolute path, it will do this. So accept path as an argument. Default is this, and the correct production grade will create this pdump. All right, save and make it executable. Now it works. Why is this version correct? Uses default argument, validates the directory, print zeros. Quick test question. Why is this unsafe? Because it starts to find all the Rust programs in a computer system. Before making this change again, we'll just create a new script, and seems nice, and we'll delete everything above or below that. Unlines 23, let's say 22 DJ and DDD. So right. Now what? chmod pdump. And let's say we call the pdump from there to this location. To this location. Project dump of this copy to clipboard. Bam. Let's see. Let's see. Yeah. How about we copy that to local bin pdump or make it global? How to make it global? Sudo cp project dump local user bin. Right. We'll do this, but this is not project dump. This is pdump, and it is found here, relative path. Instead of moving it, let's just copy it. Ah, All right. So I guess if I call PDU, yeah, I see PW. Wow, wow, fabulous. I'm so proud of myself. So this is the magic of ChatGPT and creating a script in Linux. It's damn good. Now we see all the trait.rs, main.rs. This is a main.rs. Yeah, good. Project structure is correct. Now we fix main.rs properly because what you pasted does not compile. Yeah, I know because there is no main function written over here. You have no mod declaration, no use statement, no operation in scope, add multiply in scope, ops like define outside main, missing imports. We correct this systematically. Step one, fixing the module binding. In main.rs in top, you must declare modules. Like I didn't know how to create multiple things. I never used it. Never do this. So we use Vim, create, we open up main, and it says over here, I must declare mod traits, mod traits, mod traits, and it says mod for text operation, OPERA. Operation or operations? Operations. All right. There goes our mod operations. Without this, Rust doesn't know these files exist, but these two. And step two, bring types into scope. So say use traits and then operation. So these are types and use operations multiply, add multiply. All right. So inside trait there is use traits and then OPERAEION operation. As for a different one, we'll just say use what operations add and operations operations. Uh, we have to add multiple things. So add comma multiply. All right, seems nice. We didn't use semicolon. Operation. Yeah. Now step three is fix main.rs properly. Eh? All these were also in main.rs. So main.rs properly. Replace your entire main.rs with this. So I add this. This is already there. This is already there. Now main. All right. I'll not just copy paste. I'll understand it. So we have a function add. We'll now say let let add is equals to real add and this. Then we'll say let multiply is equals to multiply. Let I thought that mod did it, but now it seems it did not. Multiply is equals to multiply multiply TIPLY. Then there is static dispatch, which is like results static add, then execute static add. All right. Let result of execute add and this is then equal to execute static static add inside this or inside function add. Then we pass 2.0 and 3.0. We add semicolon at the end, and then we what we did, paste it. Did it just automatically happen? Sorry. How to do control Z? Like I pressed U, but how to move forward now? Oh damn it. Uh, there is something called redo. Yeah. So let's yank it. Let's paste it, and instead of adding, we say mul multiply. We only say mul. All right. Mul multiply. Equation is something like what is happening here? I can't even do something with this. multiply multiply. This is happening automatically. Wow, seems colorful. And then what we do is print the static add and static multiply. All right. So now we create another line where we just print. No, print what? Print the static add, which is like this. result result, and then execute execute add, and we yank it, paste it, we go to the word, we change the word, multiply, we again go to the before that h cw mul and things, right? Do this, do that. Now dynamic dispatch with heterogeneous vectors. So this is something that I sort of did outside of the main, but here we are doing it inside the main. So I'll just delete that from you. Let's connect visual mode into how it is. Yeah. In the visual mode first of all. Now go to the visual mode. Let's go down. Done. Just DD. Not like this. I do not like it. We'll say D. How many? 1, 2, 3, 4. Let's say D3J. Yeah, we did it. Now we have to go in main. We have to paste it with a bit of a bend, bit of format here and there, and we are all good to go. and yes. Now for all right, dynamic dispatch with heterogeneous vectors. Execute dynamic or as reference, and we are doing it dynamically. All right. So let's first of all add this line where we will say we did not add comments, so let's just copy those comments. Copy it, paste it. Not like this, not like this, like this. Uh, Static dispatch over here. Copy it. Paste it. We also need line up. We have dynamic. Then we say for I in ops, isn't it? For I in no, for ops in ops iterator, for OP in ops iterator, for OP in ops iterator, I guess. Yeah. For OP in ops iter, we now create our own function which we use over here. It says that result is equal to dash dash and then println dynamic result is result. So let result equals to dynamic, execute dynamic execute dynamic. Inside that, what does it need? It needs first of all the OP. We'll give it a OP, and then it needs A. We'll give it a A. It needs B. We'll give it a B, and we'll say the end. OP as ref. All right, and we'll give some real A and B. OP dot as reference is the function. Then we give real A and B, which is 4.0 and 5.0. 4.0 comma 5.0. Then we'll cover it up, and that's it. And we print ln, we'll print the results, result. Result is the result. dynamic. Dynamic result is result. Save it. Oh, so it gets automatic formatted. So yeah, I have some automatic formatter, I guess so. Now, why operator as reference is why OP as ref. OP is ampersand, which is reference of box, which is dynamic operator. inside the dynamic operator is there. And because execute dynamic expects a dynamic operation, so box T implements dereference. So as a reference, we give it a ampersand dynamic operation. Now do this. Run cargo run and confirm the output. All right, close it and we'll say cargo and run. From here on, there are so many errors here. Why the hell are there so many errors? Somewhere I've written print. Yeah, this is what happens when you use more than one languages. Sometimes I write printf, sometimes I write print, sometimes I write print. It's not that print is wrong. It's just it doesn't give us a new line. So we need a new line. And print and println, all of them are just macros. So it needs ultra exclamation mark. But we have provided them. So yeah, we get errors. So many errors. I guess now it's done. Karuna. Building, combining, finishing. Add is 5 multiply 6, result is 9. Add 5, multiply 6, then result is 9, and then result is 20. All right. So this is what we copy, and then we paste. Why does vector dynamic operation not compile? And why does vector box dynamic operation compile? Why can static dispatch not store, add, and multiply in the same vector? Not hand waving, no hand waving. Abstraction to static becomes real. Good, it compiles, it runs, results are correct. Now you verify conceptual depth. No shallow answers. Why does think about it? Sized versus unsized types and stack layout requirements. Question 2 is why does vector it compiles? What changed? What does box provide that dynamic trade alone does not? Question 3 is why can static dispatch not store, add, and multiply in the same vector T? Why is that illegal? What does Rust require about vector element types? Answer each clearly, precisely. I don't know the answers, but I'll type something. I don't know the real answers, but I'll try. First, what does vector dynamic operation? Why does vector think about it? Sized versus unsized type, stack layout requirement. Vector is taking, let's say, dynamic operation, but then it has to move. Therefore, it only takes the reference of, ampersand dynamic operation. The reference is sized, whereas the dynamic operation is unsized, unsized, and stack layout requirements. What are stack layout requirements? Two. Why does this compile? Vector box dynamic operation compile because the box helps in dereferencing the pointer address. It becomes sized and properly navigable. What does box provide that dynamic trait alone does not? Why can static dispatch not store, add, and multiply in the same vector? If what happens if it does? It stores, add, and multiply in the same vector. What happens? P so that it becomes more organized. That's what I can say. Uh, like add is taking the same trade as the multiply, but the real compute implementation is just DIFFEI. If we do it all together, this becomes heavy and error prone. Good, you attempted. Now we correct everything precisely. We are partially circling the truth but missing core rules. We fix this rigorously. Now, why vector dynamic operation does not compile? The answer you mentioned, reference and moving, that is not the real reason. The real reason is dynamic operation is unsized. Yeah. Now, what? Yeah, I didn't know that, but yes, let's understand this. This is our theory. This is for us to understand and learn. So, dynamic operation is unsized, and Rust must know the size of every element stored inside vector t that come at compile time. Vector t layout in memory looks something like this. That requires each element has fixed size, and compilers know the size of compile time. But dynamic operation has no known size. So therefore, vector dynamic operation is illegal because dynamic operation is questionable size, like no size, unsized. How can it be no sized? It's unsized. So like str was unsized, and we were passing its length using the ampersand str. You know that ampersand str had pointer and the length for the str. So the reference was passing the length. Now, why vector box dynamic operation compiles? What changed? Now the vector stores the box dynamic operation. What is a box? A pointer. A pointer has fixed size, which is 8 byte on 64 bit. So now you store pointer, pointer, pointer. So vector can do that. Now each element is of same size, valid for vector t. The actual trait object lives on the heap. The actual trait object, which is the dynamic operation, lives on the heap. So each element is the same size, valid for vector t. The actual trait object lives on the heap. So vector store sized pointers. Heap stores dynamically sized concrete types. Now that is why it compiles, because box does not dereference to make it sized. It wraps the unsized type inside a sized pointer. Now the why static dispatch cannot store, add, and multiply in the same vector. You said more organized, which is incorrect. The real reason is Rust vectors must store elements on same concrete type. Now this is illegal, but add and type are likely the same type. Eh? Oh no, no, no. We are defining add and multiply as a different type. So how can they be same? Yeah. Otherwise, they are just arithmetic. So didn't matter earlier, but now we have made it a structure called add and multiply. So it is of different type, because add and multiply are different concrete types. Even though they implement the same trait, they are not same type. Rust do not subtype polymorphism automatically. Without trait objects, there is no common concrete type. Therefore, static, which is dispatch, requires homogeneous type, whereas dynamic dispatch allows heterogeneous type via trait object. Now I test real understanding. Answer these carefully. Why can this compile? Ampersand dynamic operation is equals to ampersand add, but this cannot. Explain in 3 precise lines. The ampersand dynamic operation is sized, which can be determined, but the dynamic operation is unsized. We are in first case taking the reference, taking the reference, which WHIC, which, so the reference can do what? Have size of its own, like str was unsized, but ampersand stored, the pointer to towards the str and the emgdf of the str. In memory, what does a trait object like ampersand Dynamic operation contains PRAIT like ampersand dynamic operation contains. What does trait objects like dynamic operation contains? The pointer of the operation dynamically. If dynamic dispatch was vtable, if dynamic dispatch uses a vtable, why is it only slightly slower and not massively slower? Answer in three precise lines. No vague language. We never learned it first of all, so don't know. But vtable lookups, how long can it be? What are vtables? Just contain a bit more process and more overhead. That's all I can guess. Now we clean this up. Why ampersand dynamic operation compiles but dynamic does not? Your intuition about ampersand str was good. The analogy is correct. Stated rigorously, like the dynamic operation is unsized type, and the unsized type cannot exist by value on the stack. Rust must know the stack size at compile time. So first point is dynamic operation is unsized type. Second point is unsized type cannot exist by value on the stack. And the third type is that Rust must know the stack size at compile time. So when you write ampersand dynamic operation is equals to ampersand add, you're storing a fat pointer sized, which is sized. So fat pointer is sized. So the actual add value still has concrete no size, and only view is dynamic. So, but this, which is dynamic operation, and we are adding add, would require placing an unsized value directly on the stack. Now that is impossible because stack layout must be fixed at compile time. So rule is unsized type must be behind a pointer. Now, what exactly is inside ampersand dynamic operation? So you answered pointer of the operation dynamically, pointer of the operation dynamically, incomplete. The trait object reference is a fat pointer which has a size. Now it contains the data pointer and vtable. I remember that. Data pointer is points to the concrete value, which is add, whereas vtable is points to the method for that concrete table, concrete type. So memory layout looks like this: dynamic operation. Inside that, we have data pointer and vtable pointer. Now the vtable contains pointer to compute implementation, possibly drop glue, and possibly size or alignment metadata. Now this is crucial. Now what is vtable? Why only slightly slow? A bit more processed and overhead, two-way is defined precisely. So vtable is virtual table, as suggested by the name itself, and a struct of function pointer is generated per concrete type implementing a trait. Example is for add, we have vtable called add compute drop. So vtable add does compute and then it drops the function. Address to the add compute and then drop is drop function. When you call op.compute ab, the dynamic dispatch does load vtable pointer, load function pointer from vtable, perform indirect call. Why only slight slow? Because it is one extra pointer dereference. It is only one indirect branch and no allocation required. if using ampersand dynamic. No interpreter, still native machine code. So overhead is equals to one extra memory load plus indirect jump. That is small related to the real computation. Now, real understanding test. Aha, so many tests. If static dispatch duplicate, there are so many tests. If three concrete architectural reasons. Mhm. I hate typing. If static dispatch duplicate code and dynamic dispatch uses vtables. So static dispatch duplicates the code and dynamic dispatch uses vtable. When would you choose dynamic dispatch over static dispatch? Give three concrete architectural reasons. So first is very known. If the you know duplication B B C M E S S T R U C T U R A heavy and more compu- computation is required for binary binary becomes too large. Then we will shift to the table that just has one extra pointer to the reference instead of giving giving space to some heavy floated binary. Uh, when would you choose dynamic dispatch over static dispatch? Where light and fast is required, then I will use dynamic PATCH, where the operation performed with too much to handle manually, then I then I will use dynamic dispatch PATCH dispatch. I think I've given enough reasons. Now, why does monomorphism sometimes improve performance beyond just removing V-table costs? Sometimes we need CCURACY as well as fast possible way. So monomorphism, monomorphization is the most direct way to it with optimized instead of just storing storing fact pointers and v table pointers. Simple in complexity, so less prone to error. Three. In large machine learning models, why is dynamic dispatch useful at architecture boundaries? Handling every operation manually manually for all the cases are nearly impossible in ML. And the dynamic dispatch is just like GHDLY heavy because of data, VDR, VDR, and because of data pointer, which is fat pointer, and V table pointer. Good effort, but still intuition level, not system level. Circling the ideas but not grounding them in architectural reality. Question one: when to choose dynamic dispatch? Your answer that is focused mostly on binary sized, that is minor reason. The real architectural reason are like heterogeneous collection. When you need vector, box, dynamic layer, dynamic optimizer, backend, everything. So heterogeneous collection, we need dynamic dispatch. Static dispatch cannot store different concrete types in the same collection. Dynamic dispatch enables runtime polymorphism. Now, plugin architecture extensibility. So when types are not known at compile time, like load module dynamically, feature flags, backend selection at runtime. So static dispatch requires compile time knowledge of types. Dynamic dispatch allows runtime substitution. Now, reducing compile time or code bloat. If you have many generic combinations, deep generic stacks, monomorphism explodes binary size and compile time. Whereas dynamic dispatch centralizes the code into one implementation path. That's it. So dynamic dispatch is about architectural flexibility, not when computation is heavy. That reasoning was incorrect. Now, why monomorphism improves performance? Your answer mentioned speed and accuracy today. Real reason with static dispatch, compiler knows exact complete type. It can inline the method, it can eliminate branches, it can perform constant propagation, it can optimize aggressively. With dynamic dispatch, compiler cannot inline through vtables. It must preserve indirect call. Inlining often gives bigger performance gains than removing one pointer load. Inlining often gives bigger performance gains than removing one pointer load. Now, that is the real reason. Question three, the dynamic dispatch in ML architecture. You said handling operations manually impossible to wait. In ML systems, you want abstraction like trait, layer, optimizer, backend, tensor operations. So you may have CPU backend, CUDA backend, TPU backend. You do not want to, match manually. That's what I said. Manual intervention is impossible. But all right, if we start matching backend with CUDA, CPU, and everything everywhere, then dynamic dispatch lets you swap implementation, hide concrete types, and maintain clean abstraction boundaries. It keeps architecture modular. Now, that is the real reason. Now we go one level deeper. This is critical. Answer carefully. Advanced question one. Why can dynamic dispatch prevent certain compiler optimizations like inlining? Uh, the dynamic dispatch should cover a wide variety of cases. So if we if try to optimize it, can not get very fast because structure is still the same. Fat pointers and v table pointers, whereas for a single pop in inlining, we can optimize the whole performance based on that operation without thinking about wide ranges of cases. Now, this is also very, you know, wide answer. It does not care to be a precise answer. Because nobody knows. I don't know right now. And it's sort of teaching me while asking a question so that I think first, it answers me next. This also can be frustrating sometimes. Like right now, I am patient, but after a few more attempts, I'll get frustrated. So, yeah. Advanced question two. Suppose you are building neural network engine. All right, I am. Which part should use static dispatch, dynamic dispatch? Answer in structured format. Static, dynamic. Uh, STATIC. Static MPL of, let's say, CUDA CPU acceleration, CUDA CPU uh, ACCL acceleration, TPU. These are all added by dynamic, dynamic. DACKEND backend services. Static can be like OPERMPI on text optimizing the TNSORS tensors. What next? Operation of text. VCTORIzation of the context every other manual PWES PRAINING of the model, reading and writing the model. Question two. I didn't answer question three. If there was there question three? Nah. Now this is also architecturally, but sharpen the precision again. Why dynamic dispatch prevents inlining? Was this the question? Why dynamic dispatch prevent inlining? I don't think so. Because why dynamic dispatch prevents certain compiler optimization, like inlining. What is inlining itself? Nobody knows. But we have an idea that it's sort of some sort of optimization. Yeah. The answer is directionally correct but imprecise. So correct answer would be with static dispatch, the compiler knows exact concrete type at compile time. With static dispatch, the compiler knows the exact concrete type at compile time. The function calls the type, the target is known. The function called target is known. The compiler can inline the function body. It can propagate constant and remove the dead branches. It can propagate constant and remove the dead branches. Yeah. The compiler can inline the function body. The compiler can inline the function body. The function call target is known. So compiler knows exact concrete type at compile time. So the compiler knows the exact concrete type at compile time. The function calls the target is known. The compiler can inline the function body and it can propagate constant and remove dead branches. With dynamic dispatch, the call target is determined at runtime by a vtable. The compiler does not know which concrete implementation will run. Therefore, it cannot inline across that boundary. It must preserve the indirect call. So the issue is not wide variety of cases. The issue is called call target unknown at compile time. The issue is call target unknown. So in dispatch, we don't know like the call target. It is not determined. It is determined by a vtable in dynamic. Whereas in static, the function calls the target. Function call target is known, and compiler can inline the function body, and it can remove dead or bad branches and constant and propagate the constants. This cannot inline across that boundary where implementation it doesn't know will happen or not. It must preserve the indirect call. It must preserve the indirect call. Now, this is precise reason. All right. Your answer has correct intuition, but needs architectural refinement. You said implementation of CUDA, CPU backends, and static is tensors, operations, training, tweaks. Now you refine it into production reasoning. So dynamic is something like backend abstraction like CPU, CUDA, TPU, layer abstraction like conv, linear, dropout, optimizer abstraction like SGD, Atom, and then plugin systems like plugin systems and device selections at runtime. All right, device selection at runtime and plugin systems. All right. Why? Because you need runtime flexibility. You may load configurations from file. You want clean architectural boundaries. Static dispatch should be used for low-level tensor math kernel, inner loop, numerical primitives, small hot path compute units, SIMD optimization, optimized operations. Why? Because they are performance critical. Inlining matters and compiler optimization matters. Zero cost abstraction is required. So now the core engineering rule is dynamic dispatch at architecture boundaries, static dispatch in hot compute paths. So where we need speed plus precision, we use static dispatch. So like calculating matrix, calculating what the tensor will be, calculating the vectors your path, calculating between two A and B's, calculating or determining some other vectorization or path or whatever model, whatever we are computing. All the compute related stuff is static dispatch. Whereas all the arrows we can optimize, we can sort of use CUDA or another models or some other prephases of those models. we use dynamic dispatches. Now, final test before we move on. Oh, please, please, please don't test my patience. Please don't. Because I am going to take a rest now. If this completes or this doesn't, I don't care. I'm going to take some rest of half an hour, something like that. I guess I don't have a opportunity to just pause this video, or else I would have. So I will just mute it and go on my business. So suppose your design is trade and then layer, and inside that we have a function called forward, which takes self and gives us input as a type tensor, and we get the return of tensor. All right. So we are taking a self and we are taking input as a tensor, and we are returning it a tensor. So we are forwarding it to a tensor. Inside forward, you perform matrix multiplication. Should you should matrix use statically dispatched? Statically dispatched. Why? Simple. If we need a speed uh, plus PRECISION, like in COMPUTES computes, like calculating matrix and other vector computes computes or tensor compute. We use statically dispatched as it is optimized, removes unused branches, keeps in line, uh, FUNC knows the call every every pitch and place. Was there any other question? No. Good. The answer is architecturally correct. Aha, you are still refining my production precision. All right. Matrix multiplication is a hot path numerical kernel executed billions or billions of times. Performance is critical if dynamically dispatched. Each multiply call would incur an indirect call. Compiler cannot inline. Loop optimization becomes limited. Auto vectorization may degrade with static dispatch. Now, concrete type is known. Compiler can inline loop unrolling possible. SIMD auto vectorization more effective. Bound checks may be eliminated. So, the dynamic dispatch at layer boundary, like static dispatch inside kernel implementation. Now, that is system. Now, that is correct system layering. You are no longer just writing Rust. You are reasoning of abstraction cost, compiler behavior, architecture boundaries, performance domains. Now we escalate. Next step, object safety. Now we do subtle move, modify your trait. All right, we'll modify our trait to this public modify. But what's modify? We are creating a cell. If we don't have if we don't have this compute, we create from self and then add that method. Then try what? Then try oops with box dynamic operation and compile. It will fail. Before you try that, predict why will this fail, because it is not unsized. Box is a pointer towards dynamic operation, so vector can store that pointer, so it is not because of that reason. But why does it fail? Why will this fail? Because self is unsized? I guess so. I guess so. Because returning self breaks the object safety? Might be. Because box cannot store traits? It can. Because it's a pointer, so it can point to anything. Because trait method must take self. Pick one and explain 3, 4. Precise line. A. Because self is unsized, incised, until the full part is known. Because self is unsized. Until full path is known. It is just creating what? Yeah, AI. Because the rate has other function create which does not take in the self but TRIES but return RETUR the type self. It seems like some error is prone to happen there. Plus the rate in itself is not fully refined because of this the TRAIT CREATE create. Good, but answer is incorrect. I know. Correct choice is B. What is B? Because returning self breaks the object safety. Now fix your understanding precisely. A is wrong because self is unsized. That is not the issue. The self in the trait is not inherently unsized. Self in a trait is not inherently unsized. The concrete implementers like add are fully sized. So the problem is not size. The real reason is object safety. The error occurs because returning self makes the trait non-object safe, not object safe. Alright. What is object safety? So trait is object safe. Why? Because it can be used behind the dynamic. Meaning the box dynamic trait must be valid. For that to work, the compiler must be able to call method via vtable without knowing the concrete type. Now, why create self breaks? If you have create and then self, you use this operation x box then dynamic operation. Now, what is self? The compiler does not know. Self could be add, self could be multiply, or something else. But trade object erase the concrete type. So returning self requires knowing the concrete type at the compile time. Now that contradicts the dynamic dispatch. Therefore, the traits with method returning self are not object safe. Now, the core rule for the object safety is a trait is object safe if method do not use self in return position unless self is sized. Methods are not generic. Method uses ampersand self or ampersand mute self or box self. Fixed pattern. You can make it compile by writing self where self is sized. Now create only available for the sized cell, sorry, concrete types or the sized cell where the self is sized. Not callable by a dynamic operation and trait becomes object safe again. Now this is critical Rust concept. Now deep understanding test. Answer precisely. Why is this allowed? But this is not. Again, returning a self. And this, it is returning a pointer to a dynamic operation which is sized. First, clone box. It is returning a sized pointer which is okay. But this is trying to return unsized, no reference cell. So this contradicts at compile, compiled PILE file line. Question 2. What are generic methods? Why are generic methods also not object safe? Generic methods like cell, value, d, explain clearly. Do something. And then we are passing self and then value p. Generic methods are too generic methods are too much uh, ABSTRACT. So no one knows the direction it will choose until it reaches some wall function or do some sort of error. Good attempt, but still considering. Why clone box is allowed but clone self is not? You said clone box returns size pointer. That is partially correct but incomplete. The real rule is when calling through a trait object like dynamic trait, the compiler must know the exact return type at compile time. Why the function clone self fails? We have, like, let's say object and then box dynamic operation, and we call the object dot clone. What is self? Self is a pointer now. Damn. The compiler does not know. It could be add, multiply, any implementer. Yeah, because it is a pointer. So yes, it can be any implementer. So dynamic dispatch erases the concrete type. So returning self requires knowing the concrete type. That breaks object safety. Now, why fn clone box with return box dynamic operation works? Because the return type is known, that is box dynamic operation. Now, this is sized, this is uniform across all implementers. VTable call knows exactly what type to return, and it does not require exposing the concrete cell. This is the difference. Why is generic method are not safe? Too much abstracted, not precise enough. The real reason is generic methods are monomorphized at compile time. Example, do something with type T self, and we are giving it a value which is again type T. Now the static dispatch, the compiler generates do something I32, do something F64, do something Spring. Yeah, because self is add, multiply, and what else? I don't know. Now, with dynamic dispatch, compiler does not know which T is used. It cannot build a vtable entry for all possible T's. A vtable requires concrete function pointers. Generic require compile time and type resolution. So generic method cannot be placed into a vtable. You must have understanding. Um, Table input HD theory loop. I am finishing the day here. Now tell me ACTL what or concept remain for the day. You covered Python. First covered is static dispatch, binary sized path pointers, heterogeneous collection, architecture boundaries, why generic breaks, object safety, and box dynamic type versus ampersand dynamic type. Plus abstraction. What remains for day 5 unfinished is dispatch benchmark. You must measure 1 million static calls, 1 million dynamic calls, and compare time. Use standard time instead. This validated abstraction cost empirically. Unit test, add CFG test and mod test, not test, add, multiply, and dynamic vector execution. Run cargo test. Proper module discipline validation. You already structured correctly, but confirm that main RS only orchestrate long lives in module, no dumping into main. Object safety note is create node.md. Write short explanation of why returning self breaks object safety, why generate break object safety, and how or where self-sized fixes it. Short, precise, no fluff. Uh, Deliverable pendings. Before day 5 is fully complete, you still owe static versus dynamic benchmark numbers, unit test passing, and node.md summary. Important. Today crossed into architectural reasoning. This is no longer syntax learning. This is the system thinking. End of the day. Submit this. Feel honestly, tomorrow we move into. Mhm. So let's end it. Bye bye. See you later.